Hello everyone. I hope that all of you are fine. Welcome to another lecture of robotics. If you remember from the previous lecture that we talked about the rotation and transformation matrices in 2 dimension. So in real world you have 3-dimensional rotations and also transformations. The real world robots are 3D. So that's why we have to learn also rotations in 3 dimensions also. Okay, so how a rotation matrix in 3D looks like. So first of all, let me draw this 3D. So let's say you have a 3D frame and you want to rotate it in the along z-axis. So this here you have your y-axis, and then you have x-axis, and here you have z-axis. So what you want to do, you want to rotate this axis along z coordinate. So after rotation, let's say if you want to rotate it in anti-clockwise direction here with angle psi. So after rotation, this will look like something. Let's say if the rotation is 90 degree, then this frame will look like something this. So here you have your z-axis, and here you have y-axis and x-axis. So this is after rotation of about z-axis. So what we did, we rotated this frame with angle psi, which is equal to 90 degree, and we get this rotated 3-dimensional frame here. So how we can write now its rotation matrix. So its rotation matrix will look like about z-axis, or we can write it like this also. Rotation matrix 3D for rotation about z-axis. So how this rotation matrix will look like something, you can call it this matrix like R, and it shows rotation about z-axis and with angle psi. This is equal to, here you have a cosine of psi and then minus sine of psi and 0, and then you have sine psi cosine of psi and 0, and then here you have 0, 0, 1. So this shows that it's a rotation about z-axis, because here you see now it has 3 coordinates: x, y, z, x, y, z. And whenever the rotation is about z coordinate, so it means that z axis will not change. You see that it's same in both of the figures. The direction is same. Only x and y coordinates, their position and orientation has been changed. So that's what we are doing here. We have a matrix here, and the x and y components, they are changing with respect to the angle psi, but the z component, it's not changing, its value is 1. Okay, and also if you want to write this in homogeneous, (3D) rotation matrix, so you can write it also like this: Rz of psi is equal to, you have cosine of psi, then you have minus sine psi, and then 0, and you have here sine psi, cosine of psi, and then 0, 0, 0, 1, and here you have to add one more column and also one more row here. So it will become a 4 by 4 matrix. So this is your homogeneous 3D rotation matrix. So just you need to add one more row and column, so it becomes a 4 by 4 matrix. And why we do that, I think we already discussed this thing in the previous lecture. We do it to make the calculations easier. For matrix multiplication, we need this homogeneous matrix to make our calculations easier. Okay, so let's see how the rotation along y-axis now look like. So rotation about y-axis. So we can write here Ry with angle phi is equal to, you have, sorry, this time we change the angle and we say that the rotation was with angle theta. So we call it cosine theta, and then we have 0, then we have sine theta, and then 0, 1, 0, and we have minus sine theta, 0, cosine theta. So this is the rotation matrix for rotation along y-axis, or rotation about y-axis. You see that here x, y, z, x, y, z. So they are arranged like this. So I'm not showing this here, the homogeneous matrix, just a normal matrix in 3 dimensions. And the y component, where the rotation has been, we have rotated about y-axis. So this is not changing. Only the x and z component, they are changing. And how much they are changing? They are changing like like we did for the z-axis here. So when you rotate your y-axis with angle theta, then your y-axis will not change, only the x and z component will rotate. Okay? And similarly, we can get the rotation about x-axis. So for that we have to write like this: Rx of phi, let's say the angle was phi, and we get like this matrix here. So here we have 1, because if the rotation is about x-axis, then x-axis will not change, only the other two axes will change: 0, 0, 0 and 0. Then we have cosine of phi minus sine of phi and sine of phi and cosine of phi. So here you see the y and z component, they are changing according to the angle phi, but the x component is not changing. So this is how we calculate the rotation matrices in 3 dimensions. And if we want to now write homogeneous, this homogeneous rotation matrix, so how we can write it? About x-axis in 3 dimensions. So this can be written as Rx of phi and simply you just have to add here 0, 0, 0 and 1. So notice what we did, that just we added one more column and one more row to make it homogeneous rotation matrix. This is we derived from here. We just added one column and one row here with 1, and that's how we get the homogeneous rotation matrix. Okay, so now let's talk about multiple rotations. Let's say we have here an axis, we call it, in 3D we have y-axis, x-axis and z-axis. y-axis, and here we have x-axis and z-axis here. So what we want is we want that we have to rotate it in such a way that we get a configuration like this. So here we have y-axis, x-axis, and it gets a little bit distorted. So here we have z-axis, and this one is your x-axis. So that's what we want. We want to reach this configuration of axis, or you can say this orientation of the axis, and we start with here. So how can we do that? We can do it using multiple rotations. So first thing we do is we do a rotation about z-axis. Okay, so the first step is rotation about z-axis. So we did a rotation of 90 degree about z-axis. Okay, and now this is how our frame should look like. After 90 degree rotation, it should look like something like this. This is X component, this is Y component, and we have Z component. Okay, so this is the rotation about Z-axis, and then we did rotation about one more rotation. It was about the y-axis, 90 degree rotation about y-axis. So we write down here, so we rotated it in a positive angle, and we call it rotation about y-axis 90 degrees, and we get this one, this orientation of our frame. So here you have the y-axis, and then you have the x-axis here, and here you have x-axis. So this is the y-axis, here you have your z-axis, and this is the x-axis. So this is after rotation about y-axis. So now what we have to do, we have to do one rotation about x-axis. Okay, so of course the positive rotation. So once we do this rotation, you see this whole frame will be now it will be move along the x-axis, and the z-axis will come here after 90 degree of rotation, and y-axis will replace this z-axis. So that's what we wanted here. We wanted y-axis in this direction and z-axis in this direction. So we can achieve this by just one rotation along the x-axis. So that's what we're gonna do here. We write down here rotation about x-axis of positive 90 degrees. So we get finally this configuration, which was our desired configuration. So that's how we can start with any configuration, and using multiple rotations we can achieve our final orientation of our reference frame. So in this case we have to first rotate it along y-axis 90 degree, and then first the z-axis 90 degree, and then y-axis, and then x-axis. Okay, and then finally we have achieved our this desired orientation of our frame. This is called these are called Euler angles. So what is Euler angles? The Euler angle says that an arbitrary rotation can be obtained by three individual rotations around the three axes. So the matrix for an arbitrary rotation can be obtained by multiplying the matrices for each single rotation. So the angles of the rotation are called Euler angles. Of rotation. So here in this case we have Euler's angles of first 90-degree rotation about z-axis, then 90-degree rotation about y-axis, and then we have 90-degree rotation about x-axis to reach the final configuration of the final orientation. So in this case, Euler angles are we have how many angles we have here? How many axes we have? We had rotation about z-axis, then we did rotation about y-axis, and then finally x-axis. And the rotations were 90 degree, 90 degree, and 90 degree. So these are the Euler angles we have here: 90, 90, and 90 degrees. And let's also write down here on the top. You can write down multiple rotations, and in this particular case we have z, y, x Euler angle rotation. Okay, now let's take an example where we have to do some transformation of the frames. In the previous lecture we have, if you remember, we did some transformations there, but it was in 2 dimensions. So in this example we shall do a 3-dimensional transformations, and let's see how we can do that. So let's say we have a frame here, but let's say here we have one frame. We call it frame A. This is y-axis and this is x-axis. And then this frame is being it's rotated and translated somewhere here. You can say, okay, I think it's too close. Let's draw it a little bit further. So here we have frame B. So this is XB and we have YB. Okay, so you see that this is frame B, and then we have a vector in this frame which is, call it, okay, something like, so this is a point P, and this vector we call it PB, because this is in your frame B. So in this frame, this vector, this point, we call it PB. I think there is some misalignment here, so let me do this correction. Let's draw it a little bit at angle. So this we call it PB. Okay, now we have these this point, this vector in your frame B. What we want that what is the value of this frame, this vector in your frame A. So that's what we are looking for, because A is the original reference frame, okay, and B is rotated frame, rotated and also translated frame. You see that this from this origin to this origin here, so there is if you remember that from the 2D example where we did some translations and rotations, so this frame is clearly translated, because if you draw here, same frame here, let me draw it with some dotted lines. So if I pick this frame A and place it here, so it will look like something like this. Okay, so this is, so you clearly this frame A has a translation. I think this is not strictly perpendicular, so let me make it perpendicular again. So now this frame is being translated here and placed at the same origin where the frame B is. So this green frame is actually, you can say, a copy of your frame A here, which is translated, but there is no rotation till yet. And then this, if you compare this green frame with your B frame, and you see that there is clearly a rotation with some angle here. If you see this angle here, so this angle theta, so there is clearly a rotation there. So we can say that frame B is rotated and translated with respect to frame A. So we have a vector here in frame B, we have a point here, and we know its position in the frame B, which is PB, which is a vector. What we want is that what is the position of this point P or vector P in frame A, which is our reference frame. Now, why we do these kinds of things, why we rotate frame, why we translate them, and why we are interested in finding the position of this point in frame A. This all has to do with robotics, robotic arm, robotic manipulators. You can consider this thing as a robotic arm, and you know its position in this frame which is rotated. Okay, imagine there is a joint here and you know its position in this frame, and now you want what is the position of this point or your end effector here, the gripper, in your reference frame. So that's why we do it. This can be useful in finding the kinematics or even also the inverse kinematics. So that's why we are doing it. So we are interested to find the position of this point in frame A. So let's draw here so we name this vector as P. Is it clearly visible, or should I draw it with some other color? Okay, let's draw it with red color. So that's what we wanted. We want this PA. Okay, so PB is given. We want PA here. So let's see what else is given here. What else is given? So the above figure shows a frame B which is rotated relative to frame A. About z-axis. Now, as I said, this is a three-dimensional example, but I didn't draw the third axis here. But you can draw it by, because the rotation is, we are taking rotation about z-axis, so that's why we haven't drawn it. But you can draw it here also if you want, like this. And here too. Is it? No, it doesn't make sense because z-axis should be parallel. So ZB. So yeah, this is the z-axis. So the rotation of this frame B, okay, is about z-axis. So this is a right-hand rule here. Right-hand rule says that if your thumb is along the axis of rotation, which is your z-axis, then your right-hand fingers will point toward the rotation. Or in other words, if you take a right hand and then the rotation, if your fingers, and if you curve your fingers and if they're pointing toward the direction of rotation, then your thumb will be the axis of rotation. Okay, so just place here your thumb, and then just, this is your thumb here, this is thumb along the z-axis, and here along x and y rotation theta will be your fingers of your hand. Okay, so yeah, so that's what we are showing here. About z-axis by 30 degrees. So the angle is theta is 30 degree, and this frame B is translated by 10 units in x A and 5 units. So units can be any units. It can be meters or centimeters in y of A. Find your position vector A, where your position vector B is 3, 7, 0, and transpose here. So clearly here you see that we have given with a position vector of frame B, which is 3 along x-axis, 7 along y-axis, and 0 along your z-axis. So this position vector B, its value is 3 and 7. It's not proportional actually, but I draw it like in a rough way. So along x-axis it's here, it's 3 along x-axis and 7 along y-axis, and z-axis it has 0. And then you have to find this position vector A. So actually what you want that what is the position of point P in your reference frame A. That's what you're looking for. And you're given with the angle of rotation of this frame, which is 30 degree. Let me write it here, 30 degree. And also you're given the translation of frame A with respect to frame B. Okay, so this is also given here. So this value here, this value and this value, they both are given. So let me write it down maybe with some different color. So let's write it like this. This green value, which is 10 units in x-axis, which is here 10 units, and along y-axis we have 5 units. So from here to here, so this origin from this origin here, so that's what we are talking about. So the translation is 10 units and 5 units between the two frames. And yeah, so we are given with these things, and what we want to find out the position vector in your frame A. In the previous lecture also we did some these kinds of calculations, but they were in 2 dimensions. This is also virtually, it's also in 2 dimensions, but we will consider also the 3rd dimension, and we shall use using the calculations, we use the 3rd dimension also in the matrix. So if you remember from the previous lecture, we did we multiplied, we developed some methods like rotation and transformation matrices, by which you can use to multiply for the transformation of one coordinate frame into other. Okay, so similarly we will do same thing here, but this time we shall use a 3-dimensional homogeneous transformation matrix. So if you draw here the so solution, if you go for solution, so the 3-dimensional homogeneous transformation matrix for rotation about z-axis. So this transformation matrix, you can call it like this: transformation from your frame D to frame A. This is equal to so what was that? We calculated in the previous slide here. So this was here, you remember, this was for rotation, homogeneous rotation along the x-axis, and then this was here. So we shall use this one matrix here. So this one here we shall use. But this is only rotation matrix, and if you remember, for the transformation, we here have the displacements values here. For example, value of about x, y, and z axis. Okay, and this here is the only rotation matrix, and if you want transformation matrix, then you have to write down here also the values of your displacements along x and y axis. So what we write down here, we have cosine. Actually here the angle we defined for rotation along the z-axis, it was psi. So let's first change the name and make it like psi, so it's easier to understand. So now we can write down here cosine psi, and then we have minus sine psi, and then we have sine psi, cosine of psi, and then because it's a three-dimensional rotation, so we also have to include the zeros here, and here 1. This one shows that this rotation is about z-axis. Okay, z-axis will remain unchanged, only the y and x-axis will change. So these values, they come from your rotation matrix that we defined previously. Here you see rotation about z-axis, cosine of psi minus sine psi. Okay, here we have sine of psi and cosine of psi. So this was rotation, and you see that here we don't have any, because this was only a rotation matrix, so we don't have x, y, and z values. Translation, they're all at 0. But for the since we are dealing here the transformation, which includes rotation plus translation, so we have to also include here the x and y values here. And to make it homogeneous, we have to add one more row containing zeros and then 1. So this one here, it shows that it's a three-dimensional rotation matrix here. Okay, so this here, I will draw something like this. So this portion here, this shows a rotation, 3D rotation. Okay, here this one, and here this shows a 3D translation, and this portion is for the you can say it's for the to make the matrix homogeneous, to which makes calculation easier. And this combined matrix, we call it a transformation matrix. So now you have this transformation matrix, and now you just have to put values here, and you have to multiply it because you're doing transformation from B to A. You have to multiply it with some vector also. So let's see. You remember that when we want to transform one frame to another, so what you need to do here, you need to multiply your frame so just put a values here. And before, we know that this relation, if we want to transform this frame here, so we can find a frame A, sorry, the vector A. If we multiply the transformation matrix from B to A with your vector B vector, so that's how we get the vector A. So you know the value of your B vector, you multiply it with transformation matrix, and you get your vector A, which is the position of your point P in the reference frame A. So that's what we wanted, we are interested in. So now here just you have to put the values. You know the value of your psi angle, and you know the value of delta x, delta y, delta z, and also you know the value of position vector PB here. So just put here these values, and you will get, just multiply them, and you will get your PA. So here it looks like something like this. PA is equal to put the values of your phi angle, and when you take the cosine it will be 0.866, and then 0.5, and here you have 0.5, 0.866, and then here you have 0, 0, and for delta x you have 10, and for delta y you have 5 here, and then 0, 0, 1, and since there is no translation along z-axis, so it will be 0, and then you just have to put 0, 0, 0, 1, and you have to multiply it with your position vector, which is what was the value of this? It was 3, and then 7, and then 0, 0. So we have added one more 0, so matrix multiplication is possible. So when you multiply this two things, we get here the value is 9 and 12.600. So this will be your position of your point in your reference frame A. Along x-axis it will be 9, along y-axis it will be 12.6, along z-axis it will be 0. So this point, if you see the position in your frame A, so it will be here 9 along x-axis, this distance here, and 12.6 along y-axis. So this is how you can use transformation matrix to transform the frames, the coordinates, and eventually you shall you shall use these things to find the position of your end effector of your robotic arm in your reference frame, because the other frames, the joint frames, they will be rotated at different angles, and what you are looking for is what's the position of this point in your reference frame. Okay, so now let's talk about a new method for forward kinematics. Forward kinematics using, we call it Denavit Hartenberg call it notation. Okay, so what is this Denavit-Hartenberg notation, and how we can use it in calculating the forward kinematics of your robotic arm? So first of all, this is a method to find forward kinematics. Okay, this is an algebraic method. To find I think find is not the right word. Solve will be better here. So we can use solve. The forward kinematics problem. You can notice that this word algebraic method. So previously, in the previous lecture, we talked about also kinematics, forward kinematics, but what the method we used there was geometric method. Okay, but this one is using algebraic method, and it is more, this method is more useful for complex scenarios, you can say, like 3D, or you can say 3 dimensions, 3D transformations. So if your reference frame is in 3 dimensions, and also there are many number of links links and joints in kinematic chain. So this method is useful when your kinematic chain or the robot has a complex is very complex to solve using geometric methods. So in this case, using geometric method will be difficult. So in this case, the geometric method is very difficult to use, especially when the situation is very complex. There is a three-dimensional rotation and translations, and also there are many number of links and frames or the joints. Then we use this algebraic technique, which is Dynamite-Hartenberg notation. So relationship between links and joints of the robot. So imagine this is the this is a two-link. We have a two-link robot. This is the previous link, and then this link. This is a link which is called link I-1, and here we have a joint which is a revolute joint, and it rotates like this. It rotates along this Z-1 axis. Okay, so this link has here a joint which connects link I-1 to link I-2. Okay, and so then link I-1, it's a little bit twisted. Okay, so here you see that on this side with joint I, it rotates about Z-1 axis. Okay, like this. But if you see on the other end here, there is a twist there. Okay, so the twist means when you take two sides of the joint and just rotate the one side and deform it permanently. Okay, now if you attach one more link here, it will not rotate like this. It will rotate about like this. Okay, because its motion is like here, like on the plane. Okay, so its z-axis will be here. So see that how we so this is called twist. Okay, link is twisted. One side is its rotation is along upward z-axis, and the other side the rotation is like 90-degree rotated, or it can be any angle, but here in case it's 90-degree. You see that this z-axis and this z-axis, zi-1 and zi, they both are 90-degree. So here the rotation will be like this, but here the rotation will be like this whole link will move about this axis, zi-1. I hope that this is clear. So we have two links here, and there is also we have two joints, which is joint I and joint I+1. And so what we did, as we talked about in the previous slide, we attached a reference frame, a coordinate system, to link to the joint I, and this reference frame, it will have a z-axis where this joint motion is. Of course, this joint rotate along z-axis like this, so we make a z-axis here, and then you have to attach the x-axis pointing toward the length of the link I minus 1. So you see that link I minus 1 is in this direction like this. So we have made the x-axis in this direction, which is x I minus 1. And then you make the y I minus 1 axis perpendicular to both of z and x-axis. So our frame 1 attachment is complete. Then what we do, we move to the link I and joint I plus 1, and we also attach a reference frame here, this red color here. So since any link attached with this joint here, it will move like in this, along this axis, z axis. Okay, so we have attached the z axis here, and we have attached the x axis along the length of this link, which is this way. Okay, and then just y axis perpendicular to both of these axes. You have noticed that here we are only concerned with z and x axis. Okay, the dh notation, it mainly focus on your x and z axis. Always the z axis will be the rotation of the joint or translation of the joint, and x axis will be along the length of your link. Now what we want to, why we are doing this, because we need a transformation matrix. We need a method for transformation of a robot. That's a simple example of having two joints and two links. Okay, but if there are multiple joints, we can also use step by step. Okay, so what we want to do here, we want to represent this frame, which is I frame, into your I minus 1 frame. Okay, that's what we are looking for. This is your initial frame I minus 1, and this is your final frame, or the next frame you can say. And what we want that, because this frame is rotated and translated with respect to this frame, so what we are looking for is to develop a method that can transform this frame into this frame, that can tell us what's the position of this frame in this frame, in the previous frame. Okay, so imagine now you have multiple links. So what you can do is you can do step by step. For example, you can transform this frame into this frame, and then here also, if there is a joint, you can then transform this frame into the previous frame, and so on until you reach your base frame, which is a reference frame, frame 0. And then in this way you can do a whole transformation of the whole kinematic chain, and you can represent the final position of your end effector in your reference or the base frame. So that's what we are doing. Previously, you remember we were doing it using transformation matrices, which were more like generalized, and they had a portion of rotation and then a vector for translation, and yeah, you just multiply these transformation matrices and you get the final answer. But in the DH convention, in the DH notation, we are using a specified method where we just want to more focus on your Z and X frames, and there are some other parameters that are important. For example, this length between the length of the frame from here to here, the length of the link I, this is important. Okay, then the next thing that's important is this theta I. Theta I is the angle between the x-axis of your previous link of the previous frame and the x-axis of your next frame. or the next link. So this x-axis xi and the previous x-axis xi minus 1. So this, the angle between them, we call it theta I. Okay, this shows that how much your your joint I is being rotated. Okay, this length of the link, this is fixed, but this theta I, this is a variable. It can change according to the rotation of this joint I. Then the next parameter is alpha I. Okay, alpha I here. Alpha I is the angle between the z-axis of the previous frame, which is zi minus 1, and the z-axis of the next frame, which is zi. So the angle between zi minus 1 and zi is called alpha I. And this is also fixed because this link is twisted in a fixed way. You cannot change it. It was made by some manufacturer that fixed the twist, because this link is made up of metal and it has a fixed shape. Okay, so it means that this angle will always be fixed, permanent. So we have our third fixed parameter, which is alpha I. So now we have three parameters which are fixed, and the fourth parameter is di here. Di is also a fixed parameter which shows offset between your link I, which is here, and the link I minus 1, which is here, and the link I. You see that these two links, they are not in a same they're not at the same height. They have different axes. The axes are a little bit they are shifted. So this length, the shift between these two, this is called di. It's also called offset, and this is also fixed because it depends upon the shape of your or the mechanical properties of your robot. So in all these things, we have one variable theta I, which is variable, and the other di, ai, and alpha I, they are all fixed. So for dh notation, we need these four parameters, which are, we need ai, we need alpha I, we need di, and we need also theta I. And these three are fixed. This is here, this is variable. So yeah, so let's move forward. And what we do, we try to create a transform here from link I to link I minus 1, creating a transform which is a transform matrix T, which transforms frame I into frame I minus 1. So what we need to do is, first we need to specify four parameters that will allow us to completely describe the transformation from one frame of the robot to the next frame. These parameters are called Danavitt-Hartenberg parameters. The one we talked about, theta I, alpha I, di, and ai. When we describe a robot using this notation, we refer it to as dh notation. So yeah, so this dh notation, this is another method for finding the for transformation or finding the forward kinematics. So here are some steps for how we can do that, how we can find the dh parameters. So the first step is rotate about the z-axis by an angle theta I, where theta I is called joint angle. So the first thing is you have to attach your z-axis to the where your rotation of the joint is. Okay, here you have attach your z-axis, and the rotation is represented by theta I, which is a variable, and this is called joint angle theta I. Second step is translate along zi minus 1 by di, where di is called link offset distance. So from here, so this axis I minus 1 it is attached to link I, and then from here to here we need a translation. Okay, so from here to here we need a translation because these two links, they are a distance from each other, then the distance is di. So with this here, with link 1 we have a joint I, we have a rotation, and then we have a translation here. Translate along x-axis by AI. This will bring the origin of the two coordinates frames together. AI is called the link length. So from here we we know that from here to the next frame, which is I frame, we have a distance of AI. So now if we want to do a transformation, we need this length. Okay, and from here then again we what we do, we rotate about x-axis by an angle alpha I. So this is x-axis, we do a rotation here and along x-axis, and the value of this is alpha I, which is constant. This angle is called the link twist angle. Here this alpha is the link twist angle, and it will align the z-axis of the two frames. So what it does, it helps to align or to relate the next z-axis with the previous z-axis. Okay, so you see that what we're doing here, we want this frame I to be represented in the frame of this link I minus 1, which is this frame here. So what we're doing here, we first try to do a rotation, that if we rotate this frame, then it will look like it will align with this axis. Okay, and then we move this frame with the distance AI, it will come here. Okay, then we again move this frame with the distance d, this frame will come here, and then once it's here, we will rotate this frame with the angle theta I. So now it will be represented in your previous frame. So this is how the DH notation works. This is how we transform one frame to another frame using DH convention. We just need these 4 parameters. So yeah, this 4 point we already covered, that rotate about x-axis. The entire process can be summarized by chaining together the 4 transformations above into a single composite transformation. So what we do, we have seen that we did 4 transformations. First, there was a rotation about z-axis with theta I. Then we did a translation along the z-axis with a distance di, multiplied by, there was another translation along x-axis, and the distance length was ai, multiplied by, we did a rotation along x-axis, and the angle was alpha I. If we these are all the matrices. Okay, these are the rotation. This is the rotation matrix. This is the translation matrix. This is translation matrix and rotation matrix. If we multiply all of them, we get a transformation matrix, okay, uh, from frame I to frame I minus 1. Okay, so you just need to, if you remember what in the previous slide, in the beginning of this lecture, we know that rotation about z-axis with angle theta, what was a rotation matrix? Homogeneous. I'm talking about the homogeneous three-dimensional rotation, and then translation, and then rotation. If you multiply all these three matrices, you get this transformation matrix, which transform your I frame into your previous frame, I minus 1 frame. So this is how we do a transformation from the next frame to the previous frame. And if you want a transformation for your complete robot having multiple joints and links, then you need to specify here the final frame and the base frame, and then you multiply them with your individual transformations. For example, if you want to do like this transformation of your frame 3 into frame 0, you have to do like this: transformation of frame 0 to 1, sorry, 1 to 0, transformation of frame to, this is multiplication, from 2 to 1, multiply by transformation of frame 3 to 2. So for each of this transformation, for example, if you want to find the transformation 1 0, okay, you should know these values, which are the DH parameters, which is theta I, alpha I, and di. These 4 parameters you must know, and then you have to put in this matrix here, and you will get this transformation. And then you have to repeat this process 3 times, and then multiply 3 of them to get a final transform of your end effector to your base frame or the reference frame. Let's see quickly an example how we can do that. Okay, let's take an example of forward kinematics using DH notation. So in the previous lecture, we studied about how to find the forward kinematics using geometric method. But this method, which is using DH notation, this is actually algebraic method. Method for forward kinematics. So what we do, we try to follow the DH conventions, and we try to find the DH, which is Dennavit-Hartenberg parameters. So let's see an example of a 2-link robotic arm. It has 2 joints, joint 1, joint 2, and then we have a link 1 and link 2 here. At the end of the link 2, we have an end effector, and this is the base link because it's not moving, so we don't consider it usually, it's fixed. So these joints, they are revolute joints, and the angle for the link 1 is theta 1, and for the link 2 it is theta 2, and the length is L1 and L2. So using the DH notation or DH convention, we assign the frames to these joints. So the first frame we assign is our base frame or the reference frame. So we want the position and orientation of this end effector with respect to this frame, reference frame. Okay, so let's assign also here a point here on the end effector for which we are interested in finding the position. So let's say the point is here. So we are interested in finding the position and orientation of this point with respect to this reference frame x0 and y0. So what we do here, we start with the reference axis, and then according to the DH convention or DH notation, we attach another frame with the joint 1, okay, this red color, and this frame is frame 1 with x1 and y1, and the z-axis of this frame is perpendicular to the x1 and y1, so it's coming out of this page or this screen in this direction. So it's not, for simplicity, it's not shown because it's in a 2D screen or 2D paper, it's difficult to draw it. So the z-axis of your frame 1, and also for the frame 0, the reference frame, it's toward you, it's coming toward you. Okay, so this is a DH convention that whenever there is a movement, or for example this is a revolute joint, so any movement should be along z-axis. So if this joint rotates clockwise or anti-clockwise, so this must be this movement toward the z-axis. So that's why z-axis is perpendicular to the y1 and x1 axis, so that the joint can rotate about the z-axis. And next what we do, we try to put the x1 axis in direction of the link length, okay, and y1 axis will be perpendicular to the x1 axis and z1 axis. So till now we have assigned two frames, frame 0 and frame 1, and they have same origin, but only the difference is that frame 1 is rotated by theta 1 with respect to frame 0. Okay, we have assigned the two frames. Now let's move toward our second joint, and now we have to again attach a frame, because here there's one more joint, so we attach our second frame here. Again, this is a revolute joint, and the motion must be toward the z-axis according to the DH notation. So the z-axis is coming toward the reader, and the x-axis, x2 axis, is toward the link length, and then y2 axis is perpendicular to the z2 and x2 axis. So to measure the position and orientation of this point, what we do, we attach one more axis here. And how we do that, we make this axis same like previous axis. So let's say this is x2 and this will be your x3, and this will be your y3. So there is no rotation, so it's almost looks same, but only there is a translation between these two axes. So yeah, so now we have assigned the frames. We have how many frames? 1, 2, 3, 4 frames. Okay, although this is not a joint, but we have assigned frame here because we are interested in finding its position So that's why we need a frame here. So according to the DH notation, what we need to do, we need to find first the parameters so that we can use this matrix here that we have calculated to find the transformation between the joints from the previous joint, from the present joint to the previous joint. So what we need all these parameters, theta I, alpha I, and then we need A, which is a link length, and we need also the offset. So once we have all these parameters, we can put in this matrix, and then we find the transform between the two neighboring frames. Okay, so once we have these parameters, for example, we can find the transformation between frame y3 to y2, and then y2 to y1, sorry, the frame 3 to frame 2, frame 2 to frame 1, and finally frame 1 to frame 0, which is our reference frame. So for that we need the parameters. Okay, so let's see how we calculate the parameters. So if you remember, this is a table, this is a DH parameter table, and in the exam it can be asked that find the DH parameters of the following robotic arm or something. So first here we have a joint, which is the variable is I, and then you have the alpha, which is the twist angle. Then you have the A, which is the distance between your z-axis of your previous frame to the next frame. So this is the z-axis of the, let's say, previous frame, and this is the z-axis of your present frame, and the distance between them is your A. And the angle between the z-axis will be your angle alpha. So let me write down here the alpha so here let's say alpha is the angle, or you can say call it twist angle, is the twist angle between zi and zi minus 1. And then you have A is the length or you can length between zi and zi minus 1. So this is the length and this is the angle. And now what is the D? D is the offset. And theta is the angle between xi and xi minus 1. So here you have, looking at this robotic arm with frames attached according to the DH convention. So what we do, we try to find the DH parameters starting from frame 0 to frame 1 to frame 2 and frame 3, or you can say joint also, joint 3. So how many joints or frames you have attached, you have to find the DH parameters for all the frames relative to the neighboring frame. So let's start with frame 1. Okay, so the parameters for frame 1, DH parameters for frame 1, the alpha, which is the twist angle, can be calculated if you consider the angle, twist angle between frame 1 and its previous frame, which is frame 0. Okay, so as you can see, there is no twist angle. They both have the same origin. The only difference is that there's a rotation, but there is no twist there. Okay, so that's why alpha is here 0. We put alpha 0 here, and then we have the one more way to find alpha, to make sure that alpha is 0, is that you see that what is alpha? Alpha is a twist angle between zi and zi minus 1. So now you are at frame 1, which is a zi frame, z1 frame, and the previous frame, which is zi frame, is the reference frame, z0. Okay, so both of these z-axes, they don't have any angle. Both of them are parallel to each other. Okay, they are coming towards you out of this screen, out of this page, and that's why when there is no angle between them, it means the angle is 0. That's why the twist angle alpha is here 0. Now let's talk about the second DH parameter, which is the length. So what is A? A is the length between the z-axis of your present frame and the z-axis of your previous frame. So as you can see that, again, the both z-axis of the frame 0 and frame 1, they don't have any distance between them. They have the same point of origin. So that is why your AI minus 1 will be 0 also, this link length. Now let's talk about the offset D. So if you remember, what was the offset D? Offset D was the distance between your previous link, which is link I minus 1, and the next link. This was a distance along z-axis. Okay, z-axis along. So, but in our case, you can see here, as both of the frames, they are at the same origin. So that's why they don't have any offset. So that is why our DI value will be also 0. Now let's talk about the fourth DH parameter, which is theta. So what is the theta? Theta is the angle between xi and x minus 1. So this is, in this case, x1 and x0. The angle between them is theta 1. Okay, so we put the value theta 1 here. So now we have find the DH parameters of your frame 1 or joint 1. Okay, with respect to the previous frame, we have found all the DH parameters, and now we move toward the joint 2 or the frame 2. So frame 2, we again try to calculate all these values, alpha, a, d, theta, but this time our previous frame will be x1, y1, z1, or the frame 1. Okay, so now let's start with this. So when we are at frame 2 or the joint 2, our twist angle alpha is, you see that the z-axis of frame 2 and z-axis of frame 1, they both are parallel because they both are coming towards you, coming out of the screen, coming out of the page, and they are parallel. There is no angle between them. Okay, so if I draw like them, it will be something like this. So they both are parallel, the z-axis, okay? zi minus 1. So they both are parallel. That is why the angle between them, which is the twist angle, this will be 0. So that's what we put in our DH table for frame 2, or the frame for the joint 2. We put alpha 0. And now the link length. Link length will be the distance between your z-axis of your present frame, zi, and the distance between your previous frame, which is zi minus 1. So the distance between z2 and z1, which is equal to L1, this is your A. So we put for frame 2, the link length is L1. Again, the offset will be 0, because there is no offset. It is assumed that the both of these two links, they are not separated much from each other, okay? And again, the angle, which is the the angle between the x-axis of your x2 and x1, this will be this angle, x2 and x1, which is theta 2. So we put here theta 2. Now we have reached till the frame 2, and now let's talk about frame number 3. Frame number 3, we calculate its all DH parameters with respect to the previous frame, which is frame 2. So the twist angle, again, it will be 0, because the z-axis of both of these frames, they are parallel to each other. Okay, they are coming out of this screen, out of this page, towards you, towards the reader. And then we have the link length, which is the distance between the z-axis of the two frames. So this distance is L2 here. Okay, so we put here the value L2, and again the offset D is 0, and because these two points are on the same plane, you can say, the same height along the z-axis. And finally, the angle theta. Angle theta is, you can say, since the angle theta is the angle between the x-axis of these two frames, which is the x3 and x2. And as you notice that the angle is 0, because both of these two axes are parallel. So here we put the value of theta is equal to 0. Is the wrong value. We put it here like 0. So once you have all these parameters for your DH table, so now it means that now you can use the transformation matrix, which was designed specifically for using the DH convention, to find the transform between the links, and finally the transform between your link 3 to your reference frame. Sorry, the reference frame 3 to the reference frame 0. Okay, so according to the DH convention, what was the transform? It's mentioned in the previous in the previous slide, but this time we show a transform which is a little bit different. So what we can do here, we can say, okay, according to the DH convention, the transformation matrix between two frames is, so now we mention this matrix again, but keep in mind this matrix is a little bit different than the previous we calculated. So what we are going to do, we're going to transform the ith frame to its previous frame, and this we can do that cosine theta I so let's write cosine as C, okay, C theta I, and we represent sine by S theta I, and then we have 0, and then we have A I minus 1, and then we have sine theta I cosine alpha I minus 1, and again we have the cosine theta. Okay, let me fill it once and then I will show you. Okay, now I have written down this matrix according to the DH convention. So what I'm going to share with you, that we already wrote this matrix here, if you remember in the previous slide, here, this matrix, but here we have written the cosine, sine, all these values, okay, and also the entities of this matrix, the elements, they were also different, especially in this area they were different, because here we were following the transformation of frames according to this pattern. For example, first rotation, then translation, then translation, then rotation. But if you follow the sequence like rotation, translation, rotation, translation, then this matrix will be different, okay. So two changes I have made here, and these changes are according to the book. Yeah, this is the transformation matrix that can be used to transform the present frame into the previous frame. And if we put values here, so put values of DH parameters in above matrix. So if you put the values here, so you will get here for the transformation of the frame, if you transform the frame 3 to 2, then you get here this matrix. Okay, let me put it again. Okay, now I have written down all these three transformation matrices. Because why they are three? Because if you remember from the previous slide, we said that if you want to do a transformation between transformation from the frame 3 to frame 0, then you need a transformation from first frame 1 to frame 0, and then multiply it with transformation of frame 2 to 1, and then transformation between link 3 to 2. Okay, so that's why we need these three matrices and transformation matrices. So each time what we do, we put values here of your, for example, if we want to find a transformation between link 3 to 2, what we do here, we put the values of your from this table here, and we put the values of of the frame 3. Okay, so let's say that we want a transformation starting from our last link to its previous link here. From link 3 to link 2, we want a transformation. We want to find the transformation matrix. So what we do, we go to the DH parameters of this link of this frame 3, which is 0, L2, 0, 0, and then we go to this transformation matrix, specially derived from the DH convention, and we put here the values of theta. Theta is 0, so cosine of 0 is 1. So here it will be 1 here. So let's put here 1, and then the next thing is you put here minus sine theta. Sine of angle 0 is 0, so we put here 0. And the next value will be 0, and the link length is the distance between the x-axis. We have already calculated link length is L2, so we put here L2 here, okay, in this place here. So our first row is complete. Now toward the second row. So if we see the second row, theta is 0, as theta here is 0, so this whole term will become 0. So we put here again 0. And for this one here, cosine of 0 is 1, so we put here 1. Okay, so the other values, again, this will be 0, this will be 0, this will also be 0, this will be again 0 because of sine, and here cosine of 0 is 1, so we put here 1, and then cosine, this term is 0, so this whole term will become 0, and then finally 0, 0, 1. So you see that the transformation between the frame 3 and frame 2 is this transformation matrix. And if you see that this portion, as we in the previous lecture discussed, this portion is a rotation matrix, 3×3 rotation matrix, and this is actually identity matrix. It means that there is no rotation between these two frames. You can verify here. If you see the frame 3 and frame 2, they are almost their x, y, z axis, they don't have any angles between them, so there is no rotation. Okay, there is only a translation along x axis, and you can see it here. This in this transformation matrix, this is along x axis. This was x, delta y, delta z. Okay, so along x axis you have L2 translation. So there is no rotation, but there is only translation along x axis, and there is no translation along y and z axis. Okay, and this homogeneous transformation matrix, using specific DH parameters, it can be used for transformation of links. Okay, so that's how we calculated the transformation between the frame 3 and frame 2, and similarly we do same thing for frame 2 to 1 and then frame 1 to frame 0. And to find the overall transformation between frame 3 to frame 0, we have to multiply these three matrices, and once we multiply them, we get the final transformation matrix, which will look like something like this. The transformation from frame 3 to frame 0 will look something like this. Okay, so now I have written this matrix after multiplication, these three matrices, and you get this matrix here. And notice that this is your final transformation matrix from frame 3 to frame 0, and according to the DH notation or DH convention. And here you see that the position of your final frame, the frame 3, is here located at, this is the position of your along the x-axis and y-axis. Okay, and this one is the rotation matrix here. So it shows that here you have rotation about z-axis. If you remember from the previous lecture, we talked about rotation about z-axis. So this is rotation about z-axis. So it means that your frame 3 is rotated according to these. Okay, I forgot to mention, C is for cosine of theta 1 plus theta 2, and then minus sine theta 1 plus theta 2, sine and cosine theta 1 plus theta 2. And similarly here you have L1 cosine theta 1, L2 cosine theta 1 plus theta 2. Okay, so this is how you're gonna read this one. And yeah, so this is the transformation matrix, and that's what you were looking for. You wanted to have the position and orientation of your end effector, your gripper, with respect to your base frame and the reference frame. So it says that your end effector frame is rotated about z-axis. You see that this is the reference axis and this is your final axis. You see that it is rotated about z-axis with respect to this reference axis, and the distance between them is the L1 cosine of theta 1 and plus L2 cosine theta 1 plus theta 2, and about the y-axis this is this value. So this is how you find the position and orientation of your end effector with respect to your base frame. So let's take another example where we have to find the DH parameters of robotic arm. So here we have a robotic arm here, and as you can see it has link 1, link 2, link 3. It has 3 links, and also it has 3 joints. So here you have a 1 joint, and the robot can rotate along z-axis. Okay, so this theta 1 angle shows that the robot rotates about the z-axis here. So this whole link can rotate. And then you have here the joint number 2, and again this link can move like in this direction with theta 2. And similarly you have one more link, it's also a revolute joint. So this revolute joint can also rotate with theta 3 angle. So now you have 3 joints. All of 3 joints are revolute joints. Okay, so we can mention here we have a robotic arm with 3 joints, 3 revolute joints and 3 links. So according to the first step, we do that to find the DH parameters. Assign the frames to joints according to DH notation. So that's what we did here. So this black color lines, they represent the actual robotic arm, and then according to the DH convention, what we did, we assigned these frames, which is frame 0, which is a reference frame, and then frame 1, frame 2, frame 3. If you remember, the DH convention says that you must have to assign the z-axis toward the direction of rotation of the link or the joint. So the rotation or any kind of movement of the robotic arm or the joint, it must be about z-axis. Okay, so that's why our z-axis is pointing upwards, because the rotation is about the z-axis. Okay, and then you can place your x0 and y0 perpendicular to in any direction. So once you assigned your frame to the joint 1, now it's time to assign a frame to your joint 2. So joint 2, joint 2, you assign the frame 1, and again the z-axis must be, the rotation must be about the z-axis. So in this case, it's a revolute joint, and if you put z-axis perpendicular to this, it's coming out of this screen or this page towards you. So this z-axis is the direction of rotation of this joint. And then, as we also did the last in the previous slide, that we place always the x1 toward the length of the link. Okay, preferably we do that. Here you see we didn't do that because the rotation must be along the axis. So in this case, x will not get priority, but if possible, try to give the link length toward the x-axis. Okay, so in this case we have a chance because the rotation is about z-axis, but length can also be placed about the x-axis. But in this case, the rotation and length both were about z-axis, so there is no chance we can put also the x-axis toward the link length. Okay, so you notice that the y-axis, it doesn't have any significance in the DH notation. Okay, so you can also ignore this axis. So we are only concerned with the z-axis and x-axis. So talking about the joint 2, we assigned here the frame 1 here, and rotation is about the z-axis and length is toward the x-axis. And then we assigned the frame number 2 to joint number 3. Again, rotation is about z2 axis and length is about the x2 axis. Then with the end point, we have assigned one more frame. Okay, you can assign it or you can also ignore it. So it depends upon what is the requirement. If it's asked that you have to find the position and orientation of your end effector, then I think it's important to assign. Otherwise, it depends upon what is being asked. So here we assigned this frame, and it looks almost similar to the previous frame, but only it's some distance apart from it. So now we have assigned the frames. Now let's start finding the DH parameters. The DH, not matrix, it's DH table parameters table is, so again you have to, how many you have, you have 1 2 3 joints. Okay, you have 3 joints here. So I've already drawn this table and now just put the values here. So starting from your joint 1, okay, which is the joint I, so we see that if we want to transform it into our previous frame, which is a 0 frame, so what we can do, we can say, okay, the frame 1 or the joint 1, for this the theta angle, which was the, if you remember, the angle theta was the angle between the x-axis of these two okay, there is a small mistake that we need to clear. So the mistake is that I mentioned that the angle theta is the angle between the x-axis of the previous frame and the current frame, but this is not true. The angle theta is actually the angle between angle about the z-axis, okay, about the z-axis of your the where the joint is rotating about. Okay, for example, we are talking about this joint here, joint 1, and theta 1 is angle about the z-axis of the frame 0. Okay, and similarly we here in the previous page we talked about here that angle x, theta is the angle between xi and xi minus 1. This is not true. The actual statement will be like this. Theta is the angle of joint about z-axis. Okay, that's what the angle is. And similarly we can also show here, so this theta is the angle about z-axis of this joint. Okay, if we are talking about here, so this angle theta, it will be the angle by which this joint is rotated. Okay, this theta I. So this is, we need to clear, this was the mistake. So now let's see how can we find the angle theta. So for joint 1 or the frame 0, it's the angle of rotation is about z-axis and its value is theta 1. So we shall just put here angle theta 1. So now the angle has been described. The second thing is we need to define the offset d. So since there is no offset, so there is no offset, we can call it the offset is equal to 0. And then we have the length A. Length A, we describe that it's a distance between the z-axis of the previous frame and the z-axis of your current frame, z1. So as you can see that these axes are perpendicular to each other, so their length cannot be measured. So that is why the length will be, link length will be 0. This is surprising for you because it looks like the length, there is a distance between these two frames and there should be a length, but this is not the case. The link length is the distance between the z-axis of the two frames. And how about the twist angle alpha? So twist angle alpha can be calculated. This is the angle between the z-axis of the two frames. So as these two angles are, the z-axis of these two frames are perpendicular, so this angle will be 90 degree. So z-axis this and z-axis this, they are at 90 degree. So for now, joint 1 is complete. We have calculated the joint angle of the joint 1, the offset, the length, and the twist angle. So now let's move to the joint number 2. For joint 2, we have the so first the angle of rotation of this joint about z-axis is theta 2. So we can just write here theta 2. And the offset again is 0, and the link length, which is the distance between the z1 axis and the z2 axis, is x1. So L1, so we can call it L1, which is actually the link length. And the twist angle alpha, so as you can see, there is no angle between z1 and z2, so this will be, its value will be 0. So now for joint 2, all the DH parameters are complete. Now moving towards the joint 3. For joint 3, we have the rotation about z-axis is the angle theta 3. Okay, and the offset is 0. The link length is the distance between the x-axis and the z-axis. Let's say this length is L2, and the twist, because the z-axis are they are parallel, so there is no angle, so this will be also 0. So this is how we calculate the DH parameters of different types of robots. And if you want to if you want further reading, I would recommend this book. For further examples, refer to the book Introduction to Robotics. And chapter is chapter 3. Okay, so that's it for today's lecture. Just practice some more, finding more DH parameters of different types of robotics arms, and yeah, so thank you very much.